Yeah, bye. Okay, great. Hello everyone. Welcome to the talk. So our speaker today is Abhranil Chatterjee. Abhranil did his PhD at IMSc, and after spending some time at IIT Bombay and IIT Bhubaneswar, he's currently an Inspire faculty fellow at IIT Kolkata, and he's going to talk about some awesome recent work on black-box randomization of rational identity testing, which in my opinion is one of the most important papers in algebraic complexity and randomization for the last maybe 5-6 years. Arvind, over to you.
Thanks, Brendan. Thanks for the introduction. Okay. Thanks for attending. I'll be presenting this recent result on de-randomizing black box variety. So this is a joint work with Arvind and Makam. They are my PhD advisors. So we are trying that problem during my PhD days. So yeah, I mean, it took around 3 years probably. Okay, so this is the plan of the talk. So I will just introduce what is this problem, rational identity testing, and then I will introduce a new model that we have used for this proof, the division algebra ABP, and briefly I will give you a proof sketch. Probably I will be able to convince all of you that our proof is correct, and how it de-randomizes the black box RIT, and I will then finish with some open problems. Okay, so in between the talks, just feel free to stop me if you have any questions. Please let me know. Okay, so probably all of you are with the PIT problem, but I will just start with 2 slides on basic polynomial testing. So PIT is just given a succinct representation of a multivariate polynomial given by an arithmetic circuit or formula or some algebraic branching program. We want to know whether it's computing a zero polynomial or not. Equivalently, we're asking that if it is zero, if it is non-zero, give me a witness of its non-zeroness, some substitution for which the polynomial will be evaluated to a non-zero value. So it is of 2 types. One is white box PIT, one is black box PIT. So for this talk, we are interested in this black box model, where we don't know how the polynomial is being computed, the circuit structure. We can only plug in some values, and it is given as the evaluation oracle. It will give us some that evaluated value, and our goal is to output a list of evaluations that would work for any polynomial that will be given. So more precisely, this list of evaluations we'll call a hitting set. So for a circuit class C, we'll say that if we have a list of evaluations, we'll call it a hitting set. If for every non-zero element in that circuit class, if it is non-zero, there will be a witness of its non-zeroness in that list of evaluations. So that's what we call a hitting set. Okay, so this PID problem has been studied in with different restrictions, like when there are some more structures on the circuit and formula, or another restriction is non-commutative PIT, where we don't we don't allow the variables to commute. So in this case, the polynomial is given by some non-commutative circuit formula or ABP, like the variables do not commute. So in that case, we treat them as 2 different strings. So for example, like how it is different from commutative PIT, like the first one, x1 plus x2 into x1 minus x2, is not x1 square minus x2 square. This is not an identity anymore in non-commutative domain, because x1, x2, and x2, x1, they're not going to cancel out each other. So in that case, when we talk about that, give me a witness of its non-zeroness, you can give me a value from the field. Field elements will not work because it can't differentiate between x1, x2, and x2, x1. So in this case, the way we define hitting set, we give a list of matrix evaluations. So for a circuit class, we say H is the hitting set. If for every non-zero polynomial in my circuit class, if it is non-zero, as a witness of its non-zeroness, I will find a matrix substitution from my hitting set. And it is known that for non-commutative ABP, even in black box, we can construct a quasi-polynomial-size heating set. It is due to Forbes and Spilka that you can output quasi-polynomially many matrices. Each of the matrices are a polynomial dimension, and that is why you can do black box PIT in quasi-polynomial-time. Okay, so probably all of you are aware with these results. So now let us introduce inverse gates in your polynomial. So in commutative case, if you allow inverses, then it computes the commutative rational function and it admits the canonical representation. Indeed, you can show that given any circuit formula or ABP, like with only polynomial blow up, you can push all the inverse gates to the top of that bundle, and you can just think of it. It is computing like ratio of it's like f by g for two different commutative polynomials. Okay, so essentially identity testing of commutative rational function, it just reduces to commutative PIT. It's independently not interesting, but this is not the case in non-commutative case. In non-commutative case, it has a rich history. In mathematics, people have been studying it. People are studying it for like last 60, 70 years. So the most interesting part about non-commutative rational function is that it doesn't have any canonical representation. Like you can't write it as like f over g or g over f, like for two non-commutative polynomials. You can't expand it as like sum of monomials. So in that case, how will you know that whether this non-commutative rational function, whether it is zero or not? So when we are saying whether it is zero or not, so just like polynomial ring or just like commutative function field, in non-commutative rational function, what do they actually compute? So they are actually elements of this free skew field. Okay, so let me also tell you one more thing. This inversion height of non-commutative rational function, just like as I pointed out, in case of commutative case, you could have pushed all the inverses to the top. In non-commutative case, you can't push all the inverses to the top. So in that case, how many inverse gates are there from leaf to root? So that also tells you how complicated a non-commutative rational formula is. And that is what we call the inversion height of the non-commutative formula. Okay, so in this case, we use this definition of, so there are many equivalent definition of non-commutative rational functions. That this definition was given by Amit Sur, that two non-commutative rational expressions, they compute the same rational function. If whenever they are defined, it may happen that rational formula is not defined on some matrix substitution, but whenever both of them are defined, they must agree. So just a simple example, like if you take 1 minus x inverse whole inverse and 1 minus x, like 1 minus x inverse whole inverse, clearly it is not defined on all the matrix substitution, but these two are actually the same rational function, because on every matrix substitution, whenever they are defined, they will compute the same value. Okay, so the RIT question, which was first formally defined by Rubens and Derksen, asked that given such a non-commutative rational formula, that you are given a formula with addition, multiplication, inverses, and you want to know whether it is computing zero in the free skew field. Okay, so for example, there is this well-known Bose identity that you can see that there is no trivial way to find whether it is computing, actually it is computing zero in the free skew field. Okay, so from the definition given by Amit Sur, so it says that two rational formulas, they're equivalent, they're computing the same rational function. If whenever you're substituting some matrix substitution, they must agree. So in following the definition, it is computing a zero function. That means that for every matrix substitution, whenever it is defined, it is zero. Or in other words, if you want to say that it is non-zero in the free skew field, you have to find a matrix substitution for which it is non-zero. So a witness of its non-zeroness, a matrix substitution. Okay, so this is the problem, that for rational formula, if you want to compute the heating set, you have to come up with a list of matrix evaluations so that whatever the tree structure the adversary gives you with addition, multiplication, and inverses within S-size formula, in your list of evaluations, you'll be able to find a matrix substitution such that if the formula is non-zero, then it is the witness of its non-zeroness. Okay, so this is all I wanted to talk about this RIT problem.
Abhranil, so I have a quick question.
Yeah.
So, for example, if you have your rational identity, or rather the rational formula to be 1 divided by whatever is there in, say, Hua's identity. Okay. So then in some sense, there is no matrix on which it is even defined.
Yes.
So what do we do in such situations? I mean, like...
Okay. So, okay, I haven't given you, I mean, all the details, how this universal free skew field is defined in Amit Sood's definition. So you have this class of all these non-commutative rational expressions, and now you define an equivalence relation that two expressions, they are equivalent if on every matrix substitution they are they give you the same value whenever they are defined. Okay, so when you are doing this, now if there is a formula which is not defined on any substitution, just like the example you gave, we call it the degenerate case, and we don't consider those expressions. That doesn't have, I mean, we call it domain of definition, like on the matrices where it is defined. And if the domain of definition is empty, we don't consider those expressions. Okay. Yeah. So yeah, any more questions? Yeah. Okay. So what is known about this problem? So in the white box case, when you can see how the formula is being computed for rational formula, it admits deterministic polynomial-time algorithm. So actually, all these algorithms, they actually solve something more general, non-commutative singular problem that I'm not going to define right now. Okay, so this deterministic polynomial-time algorithm follows from this Garg, Oliver, and Derksen. They first came up with a deterministic polynomial-time. That works only over rational and complex. Then Ivanyos, Q, and Subramaniam, they extended it over finite field. And also recently Hamada and Hirai, sorry, it's not 23, it's 21. Sorry, there is this typo. And for this black box algorithm, Derksen and Makam, they came up with a randomized polynomial-time for black box rational testing problem. Last year, with Arvind and Partha, we came up with a deterministic quasipolynomial-time for rational formulas, but that was only for inversion at 2, the first nested inverse case. So we are too far from the general case. And actually, we can observe that a rational formula can be evaluated in NC, given a matrix substitution, given a matrix of polynomial dimension, you can actually evaluate a rational formula in NC. So that puts this white box rational testing problem also in randomized NC. Okay, so this was the state of the art before our result.
So this randomized polynomial-time algorithm of Derksen and Makam, that goes via some dimension-bound matrices.
Yes, exactly. So they showed that if you have a S-size rational formula, so that means, as I pointed out, that there must be, if it is non-zero, there must be a witness of its non-zeroness. And they bound that dimension of the witness by 2s. Okay, so if you just substitute a random 2s by 2s matrix, then you can check whether it's 0 or non-zero. Okay. Yeah. Okay. So yeah, this is the result that we came up with. That it's dependent on the inversion at theta. That if you have formula of height theta, invariant SH formula of height theta, then we get a Hitten set of size ns power theta. Theta is in the exponent, log square ns, and the dimension of the matrices are ns power theta whole power order 1. Okay. Now the interesting fact is that Ruiz and Derksen showed that for any formula of sizes, you can actually bound the height by only log s. Okay, so from our result, it actually puts the rational formula, general rational formula of polynomial size. It gives a quasi-polynomial bound. So we get a quasi-polynomial size heating set for polynomial size rational formula, and therefore a quasi-polynomial time black box algorithm follows. Okay, and also as I pointed out, we can observe that that you can evaluate a rational formula in NC, and this heating set construction that we have, that can be done in quasi-NC. So it follows that the white box RIT program, actually we can de-randomize the Derksen and Makam's result and get a quasi-NC algorithm in the white box case.
So the evaluation is just some balancing, or there is more to it?
Almost yeah. So it's Brent's reduction. Rubinstein regression showed that even in this, for non-commutative rational formulas, you can do this. And to do this in NC, you just need some well-known. I mean, it's nothing special. I mean, just using some well-known results. Okay, you can. So you were asking about this NC evaluation of rational formulas, right?
Yeah.
It just follows from balancing. Yeah.
Abhranil. So I think I missed it. What is the dimension of these matrices?
Yeah, so the dimension of the matrices is again quasi-poly. So we are not giving up I mean, the matrices in your heating set, they are not of polynomial dimension. They are also of quasi-polynomial dimension.
Quasi-poly in what? In S and N.
Yeah, so n you can think of like n is bounded by s. So you can just think of s as the only parameter. So it's quasi-polynomial in s.
Okay.
Okay. Any more questions?
This is not like, I mean, it's not, so Derksen and Makam's bound, I'm guessing, was polynomial.
Yeah. So it's far from the optimal. So we know that for a sizes formula, there exists a matrix substitution of dimension 2s, and the heating set that we are getting, that is like for the general rational formula, where the inversion height is not constant, it can be as large as log s. Our dimension is like quasi-polynomial. It's far from optimal. Yeah.
I have one other question. So
Yeah.
Is it relatively, sorry, I'm completely new to this area. So is it relatively simple to see that, there's like a quasi-polynomial bound on the dimension of the matrices that would suffice?
Sorry, I'm not able to hear properly. There is some noise.
Non-zeroness, as you said. And I'm just trying to understand first, how much dimension would be sufficient?
Yeah, I think this was not known till 5 years ago.
Okay.
So we didn't know an upper bound on the.
So that's again Derksen.
That's Derksen Makam.
So is this the question that for for non-zeroness, I mean, how much is the upper bound? I mean, how much do you need to go the existence only?
Yeah, so the Akara's question was about what is there is it easy to see that there is a quasi-poly upper bound on the dimension of matrices? It's not. Right?
It's not. Yeah. Okay. So is there any more question?
Louder.
Yeah. Should I continue?
Yeah.
Okay. So yeah. So this is the result that we have, that we improve the white box complexity, and we get not improve in sense that we get a deterministic quasi-NC algorithm for white box, and for black box we get a deterministic quasi-polynomial-time algorithm using this quasi-polynomial-size heating set. Okay. So before I tell you about our proof, some proof sketch, so let me define a new model that we use in our proof, what we call a division algebra EBIT. So just probably all of you are familiar with this EBIT model, that you can think of it like some entry of this iterated matrix multiplication. So we have some we have matrix product of some, each entry of these matrices are some linear terms of sum of pi xi. Okay. Now, if this ai's are some say field entries, say from rational, and this xi, these variables are commuting, then we call it a commutative AUP. Our polynomial is some entry of this product of the matrices. We call it a commutative AUP. It is computing some commutative polynomial. If the variables are non-commuting and still the coefficients are from rational, then we call it a non-commutative AUP, and it is computing some non-commutative polynomial. Okay. So now it was first studied by Volchich, this generalized ABP model. So suppose your coefficients, these AIs, these are some matrices, and the variables are also non-commuting. Okay. So then what happens that matrices interleave in between the variables, as both of them are non-commuting. And the monomials, it looks like, so suppose the matrices are like some L by L matrices where Eij, that the basis, I mean, the ij entry is only one, these matrices. So you can think of Ej1, Q1, xi1, j2, k2. This is the most general form of a generalized monomial. So a polynomial is like sum of monomials of this form. Okay. So there is like notion where you can think of like the variables are commuting with the matrices, but here I should point it out that the model we're considering, the model which is considered by Volchich, so it was a different model, that P1x1, P2x2. This is like a different monomial from P1, P2, x1, x2. They are not going to cancel out each other, because you can find some substitution for these x variables for which you can show that it is non-zero, right? So we'll treat them as two different generalized monomials. Okay. So the model we considered, where these matrices, they are from a division algebra. So just recall that what is the extra property that division algebra has? For a matrix, you can't freely take inverses, but for a division algebra, always if it is non-zero, you know that its inverse is defined. Okay. So we consider generalized polynomial over division algebra. So the model that we have, this iterated matrix multiplication, where each entry of this matrix, AIXI, sum of AIXI, these AIs are coming from some division algebra. Okay. And we know that each division algebra has some matrix representation. So you can think of it as a special case of this generalized polynomial. Okay. And if Cjk is the basis of my division algebra T, then in the most general setting, the generalized monomials, you can write it the way it is written, this Cj1, Q1, xi1, Cj2, K2, like this. Okay. So is there any doubt on the model?
So one is, so your results are they field dependent or not? I'm asking because you have Q written here. I'm wondering if that's important.
Can you repeat which one?
The results, are they field dependent or they
okay, so we think that it is not field dependent, but I'm not fully sure over finite fields. So to be safe, I just wrote over Q. But yeah, I will check. I don't think it's dependent on field.
Okay. So that was one. The other question was, so what is a good, like, is there a simple example of a division algebra that like we should keep in mind? Because right now this looks like a
okay. Okay, that construction I haven't given it, so I don't know any. Okay, the simplest one probably the field. Field is a special case of division algebra. Okay, but other than that, there is this. So can I write? Or should I take at the end? I mean, there is like a specific division algebra construction that we use.
okay.
So for now, we are not using any special property of division algebra. We'll just use it as a separate oracle. So at the end of the talk, probably how we construct, we'll construct some divisional algebra heating set something. There we need the structure of how the divisional algebra elements looks like. So there I can tell you more about these structures. Okay. Yeah. Okay. So let me tell you the proof sketch. Sorry. Okay. So if you have a rational formula of size, whatever size, you can of say height theta, you can think of it as following. You have a non-commutative formula at the top, and then some of the nodes you're replacing with inverse of rational formula of height theta minus 1. You are composing with inverse of height theta minus 1. Okay. From the definition, you can see that you can think of a rational formula of height theta like that. So what we want to do, we want to inductively build heating set for every height theta. Some induction we want to carry out. But just notice that even if you have a heating set of height theta minus 1, that means that all these orange subformulas, that is giving you some non-zero value. But it doesn't ensure that on the inverse gate, they are defined. Because it may happen that the non-zero matrix that you got, it is not invertible. So you can guarantee that it is defined, that rational formula of height theta is defined on a point of heating set of height theta minus 1. So there we face a problem to carry out the induction. So the idea that we used, that we introduced this notion of divisional algebra heating set, that all these points must lie inside a divisional algebra. So what is the extra advantage we are getting here? As a definition of heating set, it will ensure that it is non-zero. And as a property of divisional algebra, we know that if it is non-zero, it is also invertible. Therefore, if you have constructed a divisional algebra heating set for height theta minus 1, for height theta, always you will find a point where it is defined. Okay. So with divisional algebra heating set, we can ensure this additional property that a rational formula of height theta is always defined on a heating set for height theta minus 1. Okay. So this is clear, right? Okay. Okay. So now we want to construct this heating set HNS theta. So for invariant S size formula of height theta. And for every height theta, we want to embed it inside some different division algebra. Let us call it d theta. Okay. And suppose this d theta has some, each element of this d theta has some matrix representation. Just keep it in mind, call it say L theta. Okay. Okay. So the observation, so actually it was already, this observation was already made, implicitly made in our previous paper, that if you have a rational formula of height theta, testing its non-zeroness, it reduces to this non-zeroness identity of this division algebra ABP d theta minus 1, where d theta minus 1 is the inductively built heating set of height theta minus 1. It is inside d theta minus 1. So RIT reduces to identity testing of division algebra ABP, the model that we just defined. Okay. So now our goal to carry out this induction, our goal is to construct a division algebra heating set for such d theta minus 1 ABP. Okay. So I'm just taking some time here. So just forget about the RIT problem. What we are saying, that suppose you have a rational formula. If time permits, I will show you the reduction. So just think of it, just believe that it is true. You are given as input invariant S size formula of height theta. You want to test whether it's 0 or not. Instead of that, we are saying that we are reducing this problem and we are asking that consider this division algebra ABP and check whether it is 0 or not. So when we are doing this for the division algebra ABP, we are the width will become S into L theta minus 1, and also the degree is like S into L theta minus 1. Okay. So we want to do identity testing for this model. Okay. So now the problem that we have this division algebra ABP, and we want to construct a division algebra heating set. Okay. So the first question is that, does there exist such a construction? Even existence can be argued. So what we can show that, okay, actually, if you consider this, if you can show that, like, take tensor product of two division algebra, it is not always the division algebra, but there is like a nice theory by Pierce that shows that if the index of D, call it say L, if it is relatively prime to index of D theta minus 1, then you can ensure that this tensor product, it again forms a division algebra. So this is well known. So what we show now, that this heating set of D theta minus 1 ABP for these variables N or D inside this D theta reduces to heating set construction of non-commutative ABP, where we increase the number of variables by L theta minus 1 square, and also we increase the width by L theta minus 1. So sorry, there is a typo, it's not L1, L theta minus 1. Okay.
So, Abhranil, what does index mean here? Index is the dimension in which this division algebra lives, or?
Okay, you can think of the matrix representation. Division algebra D has index L. That means each element has L by L matrix representation.
Okay.
Yeah, I mean, I don't want to use the term dimension because, like, you will see over the base field and over the extension field, it will have some two different meanings. So let us just consider the matrix representation.
Okay, sounds good.
Okay, so what we are doing, our goal was to solve this RIT problem. We reduce this problem to identity testing of this division algebra ABP. Okay, and now we are saying that this identity testing of division algebra ABP problem, we can actually reduce it to just non-commutative ABP PIT problem. And all we need to do division algebra heating set construction for this division for this non-commutative ABP, and we want to ensure that always we can ensure that the index that is relatively prime to whatever we have built, the index of the division algebra that we have already built. Okay. Okay. So let us. I'm not going into the details how we did that reduction. So just so now all we need to do that for this non-commutative ABP, given a non-commutative ABP, you want to construct a heating set inside a division algebra where the index is like some arbitrary prime power P powered L. So you can think of P is also part of your input. So if I have given a prime P as part of your input, and this you have a non-commutative ABP, you want to construct a heating set inside a division algebra where this index is like some P powered L. Okay, where does it suffice? Suppose d theta minus 1, you have used prime up to say 13. 13 is the last prime that you have used. Then what you will do? Then in that reduction, you will ask to construct a division algebra heating set for this non-commutative ABP, where the index will be of form like some 17 power something. And that would ensure that the final thing, that is again a division algebra, because you ensure that it is relatively prime to the index whatever you have built. Okay. So the division algebra heating set for non-commutative ABP for prime equals 2, it was already done in the paper that in your recent paper. So here the first non-trivial part we had to do, which is not that difficult, to generalize that construction for arbitrary prime. So more precisely, okay. before the statement, let me just show you the flowchart of our algorithm. So just assume that we have an oracle that gives me a division algebra heating set for non-commutative AVP against any prime p. Okay, by prime p I mean the index will be that p power l for that given prime p. So what we'll do, our goal is to construct a heating set for height theta. Suppose inductively we have built heating set up to theta minus 1. And as we have shown that, okay, we can now reduce this problem to heating set construction of this d theta minus 1 ABP. And now this generalized ABP heating set construction will reduce again to non-commutative ABP heating set construction with these parameters. Okay, so it shows that the division algebra heating set construction for non-commutative ABP, that is the basic building block. If we can solve that, then we can just inductively plug in everything and it would solve the heating set for height theta. Okay. So for the basic building block, the statement, so this is a weaker bound. Later we will improve this bound for the actual result. So let us start with this bound. Okay. So what we get, if we have an invariant ABP of sizes d many layers, and suppose p is also given, the prime is also given, then you can construct a heating set. The size is same like what Probst and Spilker did, but the dimension, their dimension was only d plus 1, but our dimension, to ensure that it is inside a division algebra, we need to increase the dimension of each point in your heating set, and the dimension is like nRd whole power order p. So just notice that if you have to try log s many prime, then the theta prime number you will get in up to say theta log theta. So then p will be something like log square s. So that already puts the dimension like a quasi-polynomial bound on the dimension if you want to use the prime like log s large. Okay. So using that, let us just try to bound the size of the heating set that we have. So from the flowchart, just notice that the heating set of height theta, it is dependent on heating set of height theta minus 1 and on the base case, the basic building block with parameters L theta minus 1 square n many variables, L theta minus 1 into s degree size, and L theta minus 1 into s degree. And gamma, because of, I didn't tell you the details of the reduction, because of the reduction, that gamma factor comes. It is only polynomially bounded in n and s. So we can ignore that part. And the dimension, the final dimension, is only dependent on this L. Okay. So now notice that the previous theorem, the dimension is n or d whole power order p. So here L has polynomial dependency on L theta minus 1 because the number of variables, width and size, everything involves this L theta minus 1. So we get a doubly exponential bound here on theta. So the final bound we get here, HNS theta, is like bounded by a raised power 2.
You had somewhere, you had this expression saying d theta is equal to tensor of d theta minus 1 and d. Could you have do half as opposed to doing this linearly in theta? Like, could you have written it as d theta over 2 tensor d theta over 2, something close to that?
Yeah, but so what's the source of this L theta is equal to L theta minus 1 into L? Because we write d theta as d theta minus 1 tensor product d. So that's why the dimension, it's the product of these two dimension, L theta minus 1 into L. So there you can't do any saving.
No, but if you had broken d theta as d theta over 2 tensor d theta over 2, then the bound would be better here.
Why?
Okay, a good chance I misunderstood something. But I mean, like you're doing induction linearly on theta. Is there on the inversion depth? Is there a possibility that you could do it?
Okay, so if so you are asking that from theta to theta plus 1, can we go from theta to theta? So if you can do that, then it will have some very interesting consequences. So that I will tell you when I will talk about some open problems. Okay, so yeah, I don't know, like I'm not ruling it out, but it will be too good to hope for. So whatever I have told you, like it follows that we have this ns per 2 per order theta square log ns kind of bound for the heating set. So it only gives you a quasi-polynomial-size heating set up to constant height theta. Okay, so yeah, this is the first part, like this constant height. So if you have any question on this part, please ask. After that, I will just discuss how we improve this bound.
Can we just go over this? I'm still not seeing the double exponential part. So can we
okay.
do this again?
Yeah. So okay, L has, so what is L? L is the dimension of this h at L theta minus 1 square n L theta minus 1 s into L theta minus 1 s. Sorry, not into.
Yeah.
Okay. So just see the dimension here. L is nRd whole per order p. Think of p as some constant only. Okay. So this is polynomially dependent on each of the parameter n, r, and d.
Okay.
So here L, that means is at least L theta minus 1. It is actually L theta minus 1 whole power something.
I see. Okay.
So L theta is at least L theta minus 1 square.
Oh, so every step you are at least squaring the heating set size.
Dimension. And
yeah. Okay.
And because of we're squaring the dimension, the heating set size is also like there is this huge that blew up. Okay. So now we want to control this blow up. So locally, what we want to do, we just want to improve the dependency on L of L theta minus 1. Okay. Now, in some way, if we can improve that, then that would also improve this bound on the dimension and also improve the size of the heating set. Okay. So, any question on this up to this part? Okay. So, what do you want to do here? Like, as the dimension was dependent on all the parameters, variables, width, and degree, we want to improve all the parameters one by one. Okay. So the first one, it was not that difficult. Like we used some property from algebraic automata theory and this property of division algebra that shows that you don't need to truncate at L theta minus 1 into S. You could have truncated. When I'm saying truncation, sorry. Okay, so the reduction that we showed from rational formula to the generalized AVP. So there is this. What is the degree of the generalized AVP that you need to consider? The division algebra AVP you need to consider. So there we showed that the degree that we are considering, instead of L theta minus 1 s, you could have also considered only s, not L theta minus 1. That would also then still the reduction will work. Okay, so you can drop L theta minus 1 from this third parameter degree. So dependence on degree is not a problem. But for width and variables, there we need to do some more work. Okay, so for width, what we do, this is the most technically involved part in our work. We improve that construction, the basic construction again. We got heating set of same size, but here the dimension, we made it independent of the width of the AVP. So if you just compare it with the previous statement that we had. So this is the same statement, except the dimension that we have, instead of nRT whole power order p, now we have n into d whole power order p. So even though we have L theta minus 1 into S, the width, now that L theta minus 1 doesn't play any role because we have improved the dimension. Okay. Now finally, this L theta minus 1 square in the variable, we are not able to improve that. Okay. So there a simple trick worked that for non-commutative case, what we could do that we can use the bivariate trick, like make the number of variables only 2, and that would increase the degree by only log n factor. And surprisingly, that worked for us. So just doing that bivariate trick on the previous statement, we got the it increased the heating set size by log n factor, like in the exponent. That doesn't matter for us for this quasi-polynomial bound on the heating set. And interestingly, it improves the dimension from nd power order p to d log n power order p. And now, if we now if we come to the analysis, there L has only logarithmic dependency now, because d doesn't involve L theta minus 1, and on the number of variables it is only logarithmic dependency. Okay, so L has only logarithmic dependence on L theta minus 1, we can bound L theta by ns power theta power order 1, and that also bound the size of the heating set by ns power theta log ns power something. Okay, so for the general rational formula where we know that theta can be at most log s, it bounds the heating set size by a quasi-polynomial factor. Okay, so any question on? Okay, so yeah, so let me just tell you about some open problems. So what I told you about this rational existing problem, as I told you, all those known algorithms, they actually solve something more general, the n-singular problem. And so many people are interested on this problem as it generalizes the bipartite perfect matching problem also. So the problem is the following, that you are given a linear matrix and you want to find a matrix substitution P1 to Pn. So just recall that in case of Edmond's problem, in the commutative case, we want to find a scalar substitution such that if you substitute the value, the determinant will be non-zero. Here you want to find some matrix substitution at each entry if you plug in the values, or equivalently if you take the ai tensor pi, sum of ai tensor pi, that determinant is non-zero. So that is the n-singular problem. And it is known that RIT, it can be reduced to n-singular problem. Actually, you can see, so in so many literatures, people are interchangeably using these terms that they actually sometimes they call n-singular as rational testing problem. Okay, so what do we solve? A black box quasi-polynomial-time algorithm for RIT. It doesn't give us any heating set for this n-singular problem. For the special case where this AI is only of rank 1, which captures the bipartite perfect matching case or linear matroid intersection, for that quasi-NC construction is known from the work of Fener, Gudger, Therev, these people. Okay, so our model is incomparable. You can show that like there are instances that this model can solve that we can't solve, and there are instances that we can solve that this model can't solve. Okay, so these two models are incomparable. Even we are not subsuming the bipartite perfect matching, the heating set for that, or linear matroid intersection. Okay, so as Mrinal pointed it out, that can you do this inductive stage from theta to theta? So the main problem is that the bound we got, it only works up to log s inversion height. But for in singular problem, you need to deal with like where the inversion rate can be as large as S. Okay. So if you can take care of that kind of inductive step, like where you are going from theta to 2 theta, then actually it seems like you can actually try in singular problem. Okay. So, but we don't have much idea about it. So this is the first open problem I want to talk about. And the second one is that we are getting a quasi-NC upper bound for the white box RIT. Can we get an NC algorithm for rational existing problem? Just recall that just recall that PIT of non-commutative AVP that already has an NC algorithm in white box. So it's perfectly fine. The basic building block that we are building on, it has an NC algorithm. And also it is not subsuming the bipartite perfect matching. So, I mean, okay, it's not, it will not be a breakthrough. So that is like what I hope for, like probably we'll see an NC algorithm for this rational adjusting soon for white box RIT. Okay.
So by the box algorithm for this, you mean like Forbes-Spilka is basically NC because it does this split in the middle.
So black box Forbes-Spilka, so it's quasi NC. For Das-Spilka, the Das-Spilka algorithm, that is in NC. In white box, the Das-Spilka algorithm.
Oh, I see. But that's sequential, no?
No, so it was shown in Forbes thesis. It was mentioned that it can be done. So like even using Hadamard product, Arvind, Pushkar, Srikanth, they showed that non-commutative PIT it can be done in NC2. And Probes in his thesis, he showed that even Das-Spilka algorithm can be adapted. It is an NC algorithm in white box. So we suspect that for rationalized testing also in white box, you can obtain an NC algorithm.
And the algorithm of Garg, Gurwitz, Oliveira, Derksen, so that's sequential. That's like,
yeah. All these algorithms, even that Ivanyos, all these algorithms, it's sequential. Okay. Any question?
So, Abhranil, maybe this is a silly question. I'm just trying to compare the RIT problem with the n singular problem. So the RIT problem is one where the goal is to find a bunch of matrix substitutions such that when you evaluate whatever your expression at these matrices, you end up with a non-zero matrix. Singular is not just saying that I want that matrix to be invertible, right? It's
no, not like that. So I would say that this RIT versus NC it's something similar to formula versus in commutative case, formula versus AVP PIT. Okay, so for commutative formula PIT, let us just talk about what in commutative setting. So for formula PIT, we just want to find a substitution where it is non-zero. In case of non-commutative rational formula, we want to find a matrix substitution where it is non-zero. That is exactly what we do. Something
right.
Similar to formula PIT. Now for ABP PIT, ABP problem, you can also think of it as like determinant of a linear matrix. You want to find a substitution for which this determinant is non-zero. Okay. So here, similarly, the problem is that we want to find a matrix substitution for which this determinant is non-zero. Our technique, it's the limitation of our technique. It crucially uses that the inversion height should be bounded by log s. What happened that in case of n singular problem, it was shown that if you take a symbolic matrix, if you consider its inverse, the inversion height can be as large as linear in S. It is not bounded by logarithmic in S. So for that, our heating set doesn't work for that case. Okay, so yeah, so here the challenge is to come up with something for the determinant is non-zero.
So this inversion height being like poly n or n, this was already there in Grobish vectors, like this separation between sort of.
Yeah, for symbolic matrix, the inversion height can be linear. That is actually known from work of Fortin and Reutener. I think it's early 2004,
Grobish
3 or
vector
4.
balancing for formula.
Yeah, Rubens and Wigderson used it to show exponential lower bound for Dastal's formula. Use this bound.
Okay. Thanks. Other questions? Okay. Okay. Questions from people online? Oh, all right. So if there are no further questions, let's thank. Okay.
So let's turn off the stream.
Yeah. Are you doing that? Should I?
Yeah, I'm doing that.